All right, let's start off simple today. How about some radicals? What's the square root of 9? You all best be saying, well, that's 3. No problem. How about square root of 8? Well, it's not a perfect square. However, you should remember that we could do square root of 4 times 2, which can be broken down like that, so we have 2 square root of 2. These are both real numbers. But this guy, square root of negative 16, what? What's that about? That's not a real number, you know? You can't do anything with that. But there is a whole other branch of mathematics, whole other sort of division that deals with these kinds of numbers. We've been existing purely with real numbers. And we've talked that that's the biggest set there is. Well, actually, there's a couple other groups. There's imaginary numbers. And then imaginary numbers and real numbers are members of the group we call complex numbers. And the set abbreviation we use is the C with an extra back on it. So knowing that and having that in mind, there might be something we can do with the square root of negative 16. The whole reason we have complex numbers is so that we can deal with those sorts of numbers. And it's going to look sort of like what we do here with the square root of 8. The problem is that negative, right? So the thought was, what if we wrote this as negative 1 times 16? We could then split this apart, and we have 4 times the square root of negative 1. And what was decided on a long time ago, brilliant people, they decided that in order to start doing mathematics beyond the stopping point that we had before when we reached this no real solution barrier, we would define the square root of negative 1 to be equal to I. So the square root of negative 16 is equal to 4I. The square root of negative 9 would be 3. And the square root of negative 8 would be 2I square root of 2. All we're doing is we're putting this in here also. So we'd have an extra radical giving us I along with that 2 root 2. So with this new window open to us, there's a lot of things that we can do. So let's go and explore this idea of imaginary and complex numbers. So a lot of times we use the letter Z to represent a complex number. We're going to let Z equal A plus BI. So A and B they're real numbers. So we have a number plus a number times I. The real part of Z is that A. And the imaginary part of Z is B. It's the coefficient of I. So for instance, what are the real and imaginary parts of these complex numbers? And the thing to know is that all numbers are complex numbers. Some of them will fit into the real part of the Venn diagram that I showed you previously. Some of them fit into the imaginary part. But they're all complex. Number 1 is a complex number. It has a real part and an imaginary part. So the real part of 3 plus 2i is 3. The imaginary part of 3 plus 2i is 2. Not 2i, just 2. For number 2 here, what's the real part here? This is what we call a purely imaginary number because it doesn't have a real part here. It's technically 0 minus 4i. The real part of negative 4i is 0. Purely imaginary. The imaginary part is negative 4. And part 3 here real and imaginary parts of negative 6. Remember, this is negative 6. Technically, it's plus 0i. This is why all numbers are complex numbers, because we can put 0 as the real part or 0 as the imaginary part, and we have one of these complex numbers that has a real and imaginary part. So, the real part of negative 6 is negative 6. The imaginary part of negative 6 is 0. Now, geometrically, we can look at complex numbers also. Instead of having an x and y axis, we have a real axis and an imaginary axis. If you think back to elementary school, we plotted numbers on the number line. That's our real axis. If we put in a perpendicular axis, that gives us the imaginary part of each number. And we're going to plot the real and imaginary parts of each number. So this first part, we'll call it z1, this first number, 3 plus 2i, that has a real part of 3 and an imaginary part of 2. We can show that point right there. That's our z1. The magnitude of each complex number would be the number's distance from 0 on the number line. Just like the magnitude or the absolute value, the modulus of a number is the number's distance on the number line. Now it's the distance from 0 in the complex plane in this Argand diagram. So what we're talking about is that distance. And, well, we actually have a little right triangle here, don't we? So the magnitude of z1, we use the modulus, the absolute value, just like with real numbers. It's going to be the square root of 3 squared plus 2 squared. It's the Pythagorean theorem. So this would be the square root of 9 plus 4, which is 13. That doesn't simplify. The exact magnitude is the square root of 13. I'd like you to pause the video right now, and I want you to plot these other 3. Let's call them Z2, Z3, and Z4. And why don't you find the magnitude of each also? All right, here we go, here we go. So 1 minus 4i, real part 1, negative 4 imaginary part. That's here. That's Z2. The magnitude of Z2 would be square root of 1 squared plus negative 4 squared. Parentheses around the negative 4, please. And we're going to have the square root of 17 as that magnitude. Z3, negative 1 minus I, so that real and imaginary part of negative 1. So the magnitude of Z3 is square root of 2. And then let's plot Z4, negative 3 plus 4i, negative 3 real part plus 4 imaginary part. Our Z4 would be here, and our magnitude of Z4 is going to be the square root of negative 3 squared plus 4 squared equals the square root of 25, better known as 5. So Z4 is exactly 5 units away from 0 on this complex plane, on our Argand diagram it's called. In the next video, we are going to look at how do we add, subtract, multiply, and divide complex numbers.